Welcome to Understand the Math. In this video, we're going to learn about geometric sequences, what they are, the formula we use for them, and how to apply it. We'll walk through examples to find the terms in a geometric sequence, calculate partial sums of a finite geometric sequence, and then find the sum of an infinite geometric series. And I'll also explain the difference between a geometric sequence and a geometric series. Let's begin by looking at the formula that you're going to need. In order to understand the formula, we first need to understand what a geometric sequence is. A geometric sequence is just a list of numbers where the ratio between consecutive terms is constant. I've written down an example so that we can understand what a constant ratio is. To find the constant ratio between consecutive terms, what you're going to do is you're going to take one term and you're going to divide it by the term right before it. We're going to begin with the second term, which is 6, and we're going to divide that by the first term, which is 2, and we get 3. And then the third term is 18. We're going to divide that by the term right before that, which is 6, and we get 3. And then we'll do it once again. Or we're going to take our 54, divide it by the term before that, which is 18, and we also get 3. 3 is what we call our common ratio. Whenever you have a sequence where all the numbers have a common ratio, that sequence is a geometric sequence. A geometric sequence has a really nice formula, and the formula tells us that a sub n, which is the nth term in the sequence, is just equal to a sub 1, the first term in the sequence, times r raised to the n minus 1. N is our term number, and then r is what we just found up above is our common ratio. Let's use the example that we just looked at to make sure that we understand this formula. The formula tells us what every term in the sequence is going to be equal to. Our first term is 2, and then our second term, a2, if we use the formula, is going to be a1 times r, which we found to be 3, to the n minus 1. So n is 2, so we have 2 minus 1. a1 is 2, so this is just 2 times 3, which is 6. And then let's do one more. a3 is going to be a1 times r, which is 3, to the n, which is 3 minus 1. So this is just 2 times 3 squared, which is 2 times 9, which is 18. And you can see that we have the terms 2, 6, 18 from the formula, and they match up with the numbers in our sequence. Let's now look at some examples where we're given some information and we want to find the terms of our geometric sequence. In our first example, we are going to find the first 5 terms of the sequence. Our sequence is given by the formula a sub n is equal to 7 times 3 raised to the n minus 1. Our first term is a1, so we're just going to substitute that n is equal to 1, and we have 7 times 3 to the 1 minus 1, which is 7 times 3 to the 0. Any number raised to the 0 power is just equal to 1, so this is just equal to 7. Now let's find a2. a2 is going to be 7 times 3 to the 2 minus 1, so this is just 7 times 3, which is 21. And then a3 is 7 times 3 to the 3 minus 1. You can already see a pattern here. So this is 7 times 3 squared, which is 7 times 9, which is 63. And then we're going to do something easier to find A4 and A5. We know that we have a geometric sequence. So each consecutive term is going to be r, which is our common ratio, times the previous term. Our r is equal to 3. So A4 is just going to be 63 times 3, which is 189. And then A5 is going to be 189 times 3, which is, using your calculator, or go ahead and do it by hand, is 567. Our first 5 terms are then 7, 21, 63, 189, and 567. Let's now look at our second example. We want to find the nth term of our geometric sequence. Over here on the right, to make things easier, I went ahead and wrote down the formula for a sub n. And notice, to find a sub n, which is the nth term of our geometric sequence, we need to find a1 and r. Let's look at our first example. This one, we are actually given a1 and r, so we can just write down that a sub n is equal to a1, which is 8, times r, which is 3, raised to the n minus first power. And there's our answer. Let's now look at part B. This one is definitely harder. For this one, we're given A1 and A4. Let's start by writing down our formula. Our formula is A sub n is equal to A1 times R to the n minus 1. Now let's see what we need. We need A1. We have that. And then we need R. We don't have that. So let's write down that we need to find R. The way we can find R is to use A sub 4. So let's write down our formula A sub n, and let's let n be equal to 4 so we can get A4. So we have A4 is equal to A1 times R to the 4 minus 1. A4 is 1/2. A1 is 4. R is what we need to find, and then 4 minus 1 is just 3. Now all we have to do is solve for R. Let's go ahead and divide both sides by 4. So we have 1 over 8 is R cubed. Now we need to get R by itself, so let's take the cube root of both sides. So we have on the left the cube root of 1/8, and on the right we have the cube root of R cubed, which is just R. The cubed root of 1/8 is whatever number we can multiply by itself 3 times to get 1/8. So that's actually going to be 1/2, because 1/2 times 1/2 is a quarter, times another 1/2 is an eighth. So that's our R. Now we have what we need, and we can write down our formula. We have A sub n is equal to A1, which is 4, times R, which is 1/2, raised to the n minus 1. And there's our answer. Now that we know all about geometric sequences, we're going to look at this example, and we're asked to determine whether or not the sequence is geometric. And then if it is, we need to find the common ratio. Let's look at our first one. To determine if a sequence is geometric, we need to look at the consecutive terms and see if they have a common ratio. So what we're going to do is we're going to start with the second term, and we're going to divide it by the first term, and we get 3. That's the ratio between the second term and the first term. Now let's look at the ratio between the third term and the second term. So we're going to take 45, divide it by 15, and again we get 3. And then let's look at 135 divided by 45. That is also 3. So our consecutive terms have a common ratio, and that tells us that our sequence is geometric. So let's put a yes. And our common ratio is R, and that's equal to 3. Now let's look at our next example. I wanted to include one that had fractions and that had positive and negative numbers in it. We're going to go about this the same way that we did for part A. We're going to take our second number, minus 1/2, and divide it by the first number, which is 1, and we get minus 1/2. So that's the common ratio between the second term and the first term. Now let's find the common ratio between the third term and the second term. So we're going to take 1/4 and we're going to divide it by minus 1/2. I know this is tricky because it's fractions. Dividing by a fraction is the same thing as multiplying by its reciprocal. So we're going to take 1/4 and we're going to multiply it by minus 2/1. That's the reciprocal of 1/2. And we get minus 1/2. Now let's do the same thing for the fourth term and the third term. So we're going to have a minus 1/8, and we're going to divide that by 1/4. So this is a minus 1/8 times 4/1, which is minus 1/2. And you can see that we have a common ratio for all of the consecutive terms. If you struggle with fractions, I have a video on fractions that you might want to look at. It's really quick and it really may help you. Now we need to answer the question, is this a geometric sequence? So our answer is going to be yes, because we have a common ratio, and our common ratio is minus 1/2. Now let's look at part C. We're going to do the same thing. We're going to start with the second term and divide it by the first term, and that's equal to 2.5. And then we're going to take 8, divide that by 5. If you throw that in your calculator, you can see that that's 1.6. So we can go ahead and stop because those numbers, 2.5 and 1.6, are not the same. So this is not a geometric sequence, and we can say no. Before we go on, I want to point one thing out about this problem. Notice that instead of dividing 5 by 2, if we were to have subtracted it, we could see that 5 minus 2 is equal to 3. And then if we took our next term, 8, subtracted the term before that, we got 3. And then 11 minus 8 is also 3. So this sequence has what we call a common difference instead of a common ratio, and it's actually an arithmetic sequence. I have a video on arithmetic sequences if you want to learn more about that. Let's now look at some examples where we are going to find partial sums of a finite geometric sequence. Let's first learn about what this is. A partial sum of a finite geometric sequence is just the sum of the first n terms of the sequence. We have a very nice formula for the nth partial sum. It does have a lot of terms in it, but it is a really great sum because it tells us that we can find the sum of a finite geometric sequence by only knowing the first term, the common ratio, and then the number of terms that we have. Let's now look at some examples. In these examples, we are going to find the sum of the finite geometric sequence that we're given. Let's look at our first one. We want to find the sum of all of these numbers. It's a good thing we have a formula because we would not want to do this by hand. Over on the right, I've written down steps that we can follow just to make things easier. The first step is to make sure that we have everything that we need to put into our formula. So we need to find n, a1, and r. Let's start by finding out what we have. The first term is equal to a1, so we can write down that a1 is 1. And then the last term is a sub n, so we can say a sub n is equal to 243. And then we can look at the common ratio because we're told that it's geometric, so it has to have a common ratio. So we can just take one number and divide it by the term before it to get 3. So we can say that our common ratio R is equal to 3. Now let's think about what we need. We have A1, we have R, but we don't have N. So let's write down that we need to find N. The way that we're going to find N is we are going to use the formula for A sub N. Let's go ahead and let's write that down. A sub N is equal to A1 times R to the N minus 1. And let's highlight N because that's what we need to find. Let's go ahead and plug in what we have. A sub N is 243. A1 is 1. That's kind of nice. And then R is 3 to the N minus 1. So we are solving 243 is equal to 3 to the N minus 1. Now, N is in our exponent, so we could definitely use logs to figure this out. If we don't want to use logs, what we could do is we could see if 243 is a power of 3. I think that's the approach I want to take just so that we don't have to use logs. Let's write down 3 squared is equal to 9, so let's look at powers of 3. 3 cubed is equal to 27. 3 to the 4th is 81. And then here we go. 3 to the 5th is 243. Great. So let's take this equation, and instead of 243, we're going to write it as 3 to the 5th. So over here to the left, this gives us 3 to the 5th is 3 to the N minus 1. Then we can just equate the exponents. So we can say 5 is N minus 1, which tells us that N is equal to 6. Now we have everything we need. We have A1, we have R, and we have N. Let's go ahead and let's write down our formula. S sub N is equal to A1 times 1 minus R to the N, all divided by 1 minus R. Now we're going to plug in. A1 is 1. And then we have 1 minus R, which is 3. So we have 3 raised to the N, which is 6, all divided by 1 minus R, which is 3. This is 1 minus 3 to the 6th power, which if you use your calculator is 729. And we're going to divide this by minus 2. So this is minus 728. All divided by minus 2. Let's come up here because we're running out of space. And this is equal to 364. And there's our sum. Let's now look at another example. This example looks very different. Sometimes when we have a sequence, we are given the sequence in this form and not given the individual terms. But that's okay because it still has everything that we need. Let's look at our steps over here to the right. Our first step is we need to find N, A1, and R. So let's do that. N is the number of terms that we have. Because we have a 6 sitting up on the top here, that means that we have 6 terms because our first term started with 1. So we have 1, 2, 3, 4, 5, 6 terms. So we can write down that N is 6. Now we need to find A1. To find A1, we are going to substitute 1 into this formula for K. So this is 5 times minus 2 to the 1 minus 1. So this is 5 times minus 2 to the 0. Any number to the 0 is just 1. So A1 is equal to 5. And then let's see, what else do we need? We need R. R is our common ratio, and that's just equal to negative 2. So let's write down R is minus 2. Now we're good to go, and we can just go ahead and find S sub N. Here's our formula. S sub N is equal to A1 times 1 minus R to the N, all divided by 1 minus r. Plugging in a1 is 5. And then now we have to plug in r. So we have 1 minus r, which is negative 2. N is 6. And then in the denominator, we have 1 minus a negative 2. Lots of negatives going on here. This is 5 times 1 minus negative 2 raised to the 6th power. That's actually equal to 64. And then in the denominator, we have 1 minus a negative 2, so that's 1 plus 2, which is 3. Let's come down here to the lower left. This is then 5 times minus 63 divided by 3. Let's divide 3 into 63. So this is just 5 times minus 21 gives us a total of minus 105. And that's what our sum is equal to. The last examples that we're going to look at are examples where we're going to find the sum of an infinite geometric series. Notice it's a series and not a sequence. Let's first find out what an infinite geometric series is. An infinite geometric series is the sum of all the terms in an infinite geometric sequence. I've written down here an example to make this easier. An infinite geometric sequence is just a list of numbers, such as 2, 6, 18, 54. We actually looked at this example before, and the common ratio in the sequence was equal to 3. Now we have an infinite geometric series, and it's those same numbers, but we're going to add them instead of just list them. We often want to find the sum of an infinite geometric series, and we can do that if the absolute value of the common ratio r is less than 1. Let's look at this. When the absolute value of r is less than 1, we have a formula to find the sum of an infinite geometric series. Before we get to the formula, I'll go ahead and put it so you can see it here in green. Let me just show you quickly where it comes from. We start with s sub n, and then if we have an infinite series, our n is going to go to infinity because we're going to have an infinite number of terms. So what happens is this n right up here is going to go to infinity, and r to the n is going to go to 0. Let's see exactly why that is. For example, if you have r equal to 1/2, you're going to have 1/2 raised to a large number. That's just like 1 divided by 2 raised to the large number. 2 raised to a large number is just a large number. And then if you divide 1 by a really big number, it's going to go to 0. So the great thing is that this term is going to go away. And we're left with a formula that I've written down here in green. Our sum is just a1 divided by 1 minus r. And remember, this only works if the absolute value of r is less than 1. If the absolute value of r is greater than 1, then we say that the series diverges. All that means is that it just doesn't have a finite sum. Let's now look at some examples. We are going to find the sum of an infinite geometric series that we're given. Here's our first example. We're given the series in summation notation, and we want to start by writing down the formula. Our formula is S is equal to A1 all divided by 1 minus R. Now, we need to find A1. One of the most common mistakes I see students make is to just look up at this and say, oh, 10 is our first term. It's actually not. Let's go ahead and let's write down what these terms are equal to, at least the first two. Our first term is going to be 10 times 4 over 5 to the 1. And then we're adding because we have the sigma. So then we add 10 times 4/5 to the 2, and then all the other terms. So our first term is 40 divided by 5, which is 8. And then it doesn't matter what the other terms are. So 8 is actually a sub 1. And then our common ratio r is 4/5. Now we can go ahead and plug this in. So our sum is going to be 8 all divided by 1 minus 4 divided by 5. Let's do this fraction first. We can think of 1 as 5 over 5. So we have 5 over 5 minus 4 over 5. This is 8 divided by 1 over 5, which is just 8 times 5, which is 40. So our formula tells us that the sum of this infinite geometric series is equal to 40. It's a great formula. Now let's look at our second example. One thing that I want you to notice about this example is r. r is equal to 5/3. That is greater than 1. And whenever we have an infinite geometric series with a value of r greater than 1, our series does not have a finite sum, and we say that the series diverges. If you go on to study calculus, you will study series just like this. And that's it. You now know all about geometric sequences and how to find their terms and partial sums, and also know about infinite geometric series. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.